Thank you. Yeah, and thank you for the organizers. So yeah, I'm going to be talking about interacting dark sectors in cosmology, and in particular, I'm going to be talking about uh, dark sectors with interacting dark matter and dark radiation. So just to first talk about some motivation. So why are we looking at interacting dark matter and dark radiation? Um, so I guess when it comes to the question of what new physics might we expect from a theory perspective, and effective or extra radiation is a pretty generic feature of many new physics models. In particular, if you have new degrees of freedom at high energy in the dark sector, you might expect in many BSM models that they'll predict some extra light degrees of freedom, and this will contribute to an effective. So it's a general way to parameterize uh, a large class of BSM models, and then if we can understand what the effects of an effective are in cosmology, we can better understand a general constraint on BSM models from cosmology. Um, and then when it comes to dark matter interactions, so if we're talking about interacting dark sectors, we might expect that you have some interacting dark sector with dark radiation, as well as some massive component which would contribute to dark matter or be all of the dark matter that we see today. And so depending on the mechanism for dark matter production, if it's a freeze out model of dark matter production, you might expect, depending on the freeze out mechanism, that there remains some interaction between the dark matter and the dark radiation. Either if you have multiple components of dark matter, then there could be a strong coupling between the dark matter and some other uh, light relic in the dark sector. Or if it's all of the dark matter, you might expect a weak coupling between the dark matter and some other radiation particle in the dark sector. And then another main motivation for looking at these class of models is motivated by what were tensions in cosmological data. So the main motivation was Hubble, so the Hubble tension, and in large scale structure there were, but are not is not so prevalent, but there was the S8 tension and some Lyman alpha tensions, which suggested suppression in the matter power spectrum. And so these were motivations for looking at these class of dark matter, dark radiation um, models, but we still want to understand what constraints there are and if they're still motivated to be interested in. So just starting with light relics, so just to give you an idea of where we are, the sort of the minimal extensions of the lambda CDM model include ineffective. So this is obviously something people have looked at for a while, and so most of these will just assume that ineffective is free streaming, and so the minimal extensions, if you have just one new degree of freedom in a scalar or a fermion or a gauge boson, give these values of delta n effective. And so the forecasts for future sensitivity are keeping these in mind. So Simon's observatory is expecting something like 0.05 when it comes to n effective. Um, and keep in mind, these are all for free streaming radiation. So uh, the bounds can change. The delta n effective values will stay relatively the same, although if you have an interacting dark sector, you might expect that there are other mass thresholds due to other particles, and so these numbers could change slightly as well. And so the main focus of this talk will be that we're already seeing significant constraints from the new data from ACT-DR6. And so we want to understand how generic these constraints are, if they're true for only free streaming radiation or interacting radiation, or some other class of radiation models, which we've looked at for the Hubble tension. And so I'm going to talk about just the Hubble tension, since the Lyman alpha and SA tensions are not so significant anymore. So just to give a brief overview, um, so when it comes to models that are trying to address the Hubble tension, the main idea is that the CMB pretty precisely directly measures this value theta s. And so this is something that we want to keep fixed, but because it's an angular scale, it's a ratio of two physical scales, the sound horizon RS, and then the angular diameter distance, which I'll just say something like the distance to the CMB, and this physical sound horizon, of course, corresponds to size of fluctuations in the CMB as well as in BAO. And so the idea with addressing the Hubble tension, as I mentioned, is to keep theta s fixed. Um, and so the class of models I'll talk about are early time solutions to this. So the idea there is you want to keep theta s fixed, but decrease RS and make no changes to the late time expansion history so that H naught will compensate for your change in RS. And so just looking at the equation for RS, the way to reduce RS would be to add some extra energy before recombination. So this is just a plot of the different energy densities um, in the standard model. So we have radiation, which is composed of neutrinos as well as photons, and then some CDM and baryons, which contribute to matter as well as cosmological constant. So as I mentioned, the idea is to add some extra energy density before recombination. Um, what often happens is that since you don't want to change the late time history too much, you don't want to add the extra energy density too near recombination. So often a lot of these models will sort of significantly impact the expansion history around equality. So around this scale here, and then will either dilute away the energy density so as to keep this distance fixed. And so the simplest solution we could think of is since at these early times, most of the energy density is already in radiation, the simplest solution would be to add some extra form of radiation. And so that's the motivation for these interacting dark matter, dark radiation models. And so the outline, I'm going to just talk about two models of interacting dark matter and dark radiation that were introduced to address the Hubble tension as well as large scale structure tensions, and then some cosmological signatures of those models, and then just briefly talk about the constraints from ACT on ineffective currently, and then some preliminary results from our current work on updated constraints on these interacting models from ACT. So the first interacting radiation model that I want to talk about is to talk about interacting radiation that's self-interacting, and then the simplest thing we could add is a massive mediator. So this would be the Lagrangian for that. And the idea is we have these fermions, which are the dark radiation. And then we also have this Yukawa coupling to a scalar phi, which has a mass that's around eV. And so when you reach the mass of the scalar, the scalar will decay into the other light particles. And the change in the degrees of freedom will increase N effective at whatever this mass threshold is. So you'll have a smaller N effective early on near BVN, and then a larger N effective later on, which will contribute to the increase in decrease in RS. And then another sort of interaction we can add is between the dark matter chi here and our scalar phi. So we just added another Yukawa coupling for simplicity. And so then the interaction that you get is this T-channel scattering between our dark matter and our massless fermion. So this is the dark radiation, um, and it's mediated by our scalar, which has a mass around eV. And so this is just to sort of briefly go over what the dynamics of this looks like. So at uh, early times, we have the relevant interaction between our dark matter and our dark radiation is this T-channel scattering. And so for cosmology, the relevant parameter is going to be this momentum exchange rate between the dark matter and the dark radiation. And that scales importantly as T squared, so the temperature of the dark sector over the mass uh, of our dark matter. And as you can see, there's some degeneracy here. So the mass of the dark matter and the interaction strength. And so compared to the standard CDM picture, what you have is early times, you'll have some extra pressure to the dark matter that comes from this momentum exchange between the relativistic particle and our standard cold dark matter. And so early on, so this is before um, equality, you'll have some suppression of the growth of matter perturbations that results from this extra momentum that the cold dark matter gets. And then once you reach the temperature of your mediator, so that's the scalar particle, um, we get this effective operator, which importantly has a T over M phi to the fourth suppression. And so effectively the dark matter interactions will turn off. And so you get essentially just CDM with some extra velocity. And so yeah, the main idea behind this was really to sort of address um, the S8 tension, because you get some sort of small suppression early on in the structure growth, and then at later times you get regular CDM. Um, you would produce some phi, but it would be suppressed, right? So you wouldn't have like a thermal population of phis, because they would just quickly decay to the light scalar. Yeah. So this one's, we just said, is massless. Yeah. And so then just to sort of show the effects of this, um, the effects of the dark matter, dark radiation interactions are that you get this smooth suppression in the matter power spectrum at smaller scales. And so this suppression is proportional to log K, and it's proportional to the interaction rate between the dark matter and the dark radiation, which is a free parameter. And so the interaction rate will tell us essentially what the slope of the suppression in the matter power spectrum is. And then the scalar tells us when these interactions shut off. And so we can sort of translate that to a redshift at which the dark matter is not interacting anymore, and that corresponds to a K scale here. And so you can see, depending on the different masses, you'll see suppression starting at different scales. Um, and so these are just the constraints that we looked at from Planck and Lyman alpha. So this is obviously showing the sort of older Lyman alpha EBOS um, likelihood, which is changed, so it's not relevant, but I just wanted to show the current constraints on N effective and H naught in this model. This is with the shoes prior, obviously, but what we find is that it's not correlated with the interaction strength here. And so you can, in theory, solve H0 without affecting large-scale structure significantly, which was an original problem with many of these models that didn't have this sort of massive mediator. Okay, and then the other model that I want to mention, which I'll just go over briefly for time, but also simplicity. So it has many of the same features, but it's called neoatomic dark matter. So very similar to the sort of standard atomic dark matter. The sort of key feature that's different is that the radiation component remains strongly interacting the whole time. So the dark sector in this model is a what they're calling a dark photon, and then a dark electron and a dark proton. And so the dark electron and the dark proton plus whatever the dark atoms are will contribute to some fraction of the dark matter. And then the radiation, which is this dark photon, will contribute to the radiation component. And so you'll get this, so you won't get the change in net effective in this model, but you will get that the interactions will between the dark matter and the dark radiation will turn off when you get to this dark recombination scale. And so just showing some of the effects of this model on the power spectrum. So similarly, you get, so yeah, I should mention, yeah, so in this model, obviously the atomic dark matter is just a small component of the total dark matter. And so in this model, you'll get features that look like a suppression, but also because you have a strongly interacting component of the dark matter, you get dark acoustic oscillations near where the decoupling redshift is. And then you also get this suppression of the matter power spectrum, where the strength of the suppression depends on the fraction of dark matter that you have that's interacting. And then the scale at which the power spectrum suppression starts is related to the scale of your dark recombination. So that's related to the mass of the electron and proton here. And then also looking at the CMB, the sort of key features here that you'll get in addition to just the normal effect of extra radiation in the CMB is that the fraction of dark matter will give you also this constant suppression at from medium to low L, or sorry, larger L's, related to the strength or the fraction of dark matter. And so this L dependence to the suppression is different than the L dependence that you would get from just extra radiation. And so this is probably the reason that we think it fits better to the CMB and allows for larger amounts of radiation compared to just a standard interacting radiation. And so these are the fits from here, from the, so this is Planck plus just BAO. And then this is adding the H0 prior. So here we see that this model works slightly better at resolving the H0 tension. Although when we add the F data set, so this is adding just the full shape data from BOSS, there is just sort of comparing these two, there's a little bit of tension here with full shape. And we think that's because many of these models will predict a larger NS, which I mentioned, which I'll mention later. And so that large NS can have conflicts with BOSS, which BOSS full shape data, which measures NS pretty precisely. Okay, so then just to summarize what some of the cosmological signatures are. So the effects on the CMB, which are pretty known for extra radiation, is that you get silk damping at high L's, as well as this phase shift. And both the silk damping is a pretty generic feature of just extra radiation, while the phase shift will depend on whether that radiation is interacting or free streaming. And then additionally, if you have dynamics in your dark radiation, so the massive mediator, as I mentioned, that can alter these effects a little bit. And so that's sort of the motivation for also fitting these models to act to see if the constraints are sort of generic for most radiation models. And then just to summarize the large scale structure interactions, the large scale structure effects come from the dark matter interactions with the radiation. And so in both models, we predict a suppression of structure formation at small scales. If it's weakly interacting, it'll be a smooth suppression of the matter power spectrum. And then if you have a component of dark matter that's interacting strongly, then we also predict something like dark acoustic oscillations at smaller scales. Okay, and so just to look now at what the current ACT constraints are on free streaming. So this is just for ineffective free streaming. The current constraints for ACT with just Planck is 2.73, and then when you add lensing and BAO, we get a slightly larger and effective. And so yeah, this is probably due to the fact that DESI, so the BAO data that they're looking at is DESI BAO, and so if you have a low and effective, then you'll also have a lower amount of omega matter just to keep equality fixed, and so DESI has a preference for a value of omega matter in their data, and so this sort of difference is likely due to what is the tension in lambda CDM between DESI. And so, yeah, so just looking at the constraints here, it seems like, so the scalar is out at 94%, and the spin, the fermion is out at 99%. So this would pretty much kill I think most extra radiation models, just kind of looking at these results and taking them seriously. And so what we want to understand is how generic is this for also the other dark radiation models. And so they also did a fit with self-interacting dark radiation, and it seems that they're getting sort of similar constraints. So this orange is just Planck, and then adding in ACT here, we get significantly stronger constraints on the amount of interacting radiation. And so these are new fits that we did with looking at our interacting dark radiation with the massive threshold. So these were in blue is the constraints that we had from Planck, where we would go out to 0.6 at about 99%, and there was like a small preference for some dark radiation. And here with Planck, I mean with ACT, we're seeing almost all of that is gone. So it seems like even for the extra radiation with the massive mediator, that we're still seeing significant constraints on dark radiation models here. So this is likely due to silk damping, which I'll show in another plot. But just looking at the sort of residuals, we see that DR6 shows enhanced power at small scales, even relative to lambda CDM. So that's where ineffective is just 3 in TT, and also to some degree, I think, TE and TT. And then a sort of open question that we have, I mean, these are all just preliminary fits, but sort of looking at the forecast, we expect that CMB lensing will take over the effect at very small scales, where silk damping is significant. And so the question is if we need modifications to the lensing codes that are used there when fitting with modified dark matter models. In particular, I think some of the models we've been using don't affect the late time dark matter structure, so we've assumed that it's fine to use those, but the more significantly modified dark matter models might need to consider how much of lambda CDM is baked into the lensing codes. And so this is also, I just wanted to show also the preliminary um, results from new atoms. So this is the atomic dark matter, which was sort of working even better than this model at solving the H naught tension. And here we get similar results uh, to the interacting radiation with the massive threshold. So it seems like uh, it is a pretty generic feature of ACT that it really does not want any power uh, or any suppression of power at these scales, at smaller scales. And so just to, I mean, we're still trying to find out exactly if that's what it is causing the constraints in the fits, but so this is preliminary, but the idea is that the damping scale is also proportional to H naught. In particular, R D, so the damping scale over RS is proportional to square root of H. And so if you try to change RS in order to keep theta S fixed, you will get that the damping scale will change proportional to Hubble. So basically you can't keep both theta S and theta D fixed at the same time because they have different relations to Hubble. And so a common thing that will happen is that NS is used to compensate in these fits for the extra damping of structure at small scales. So this is just showing a plot of an effective. And so here we're just varying an effective just to show that the damping structure. And then you can sort of concoct NS values that will sort of keep the structure fixed at small scales. The issue is that, of course, you have to pick a particular pivot scale to calculate how to keep this fixed. And NS is a power law, and the silk damping is an exponential. So eventually, when you get to smaller scales, NS stops working as well. So you can basically use the power law NS to keep some range of L's fixed, but eventually you the exponential will win out in the end. Yeah, so if you just change NS, then yeah, you'll still have trouble in the low L. So usually you'll also see a L smaller. Yeah. I mean, so you'll also see changes in other parameters, so like the baryons, and then um, mostly baryons and dark matter as well. So that'll compensate often for the lower effects, the low L effects, although not entirely. But yeah, so eventually you'll see, yeah, some combination of a lot of things moving to try to compensate for it. And so, yeah, so we are still trying to understand if this is just a feature that we'll see in basically all models that are trying to solve the H naught tension by adjusting RS to keep theta S fixed. So only doing an early time solution. Since in all these models, you'll see that you'll change the damping scale. And so eventually you will get enhanced damping at small L's. And just looking at the other models that were fit to ACT, it seems like that's roughly what's happening, is that they'll predict larger NSs to compensate, but then when you fit to ACT, it doesn't work as well. And then there's another sort of thing that to worry about in a lot of these models when fitting is that if you have an extension of lambda CDM, that this can have issues when you're doing a sort of Bayesian analysis due to the effects of your extra parameters. So essentially when your extra parameters sort of go to zero or go sort of are continuously connected to lambda CDM, then they have no effect, but they will give you enhanced volume. And so that is to say that the Bayesian analysis is going to be very sensitive to whatever your priors are on those extra parameters. And so people have been looking at doing a frequentist analysis as well, just to see what the difference is. And so there they'll just compute these 1D profile likelihoods. And so this is, I'm just showing one that was done for EDE, because here you can see, so this is the 1D profile using the frequentist model, and then this is from just the Bayesian analysis posterior. And so these two, uh, sorry, these are the two issues have significant, or I mean, pretty significant differences, assuming, and these are just as it's the same data. And so yeah, so the idea is that, you know, if you have posteriors, which are significantly non-Gaussian, and in particular, this is usually the case when looking at these H0 posteriors, because you'll have like a sort of a tail that goes out to larger H0 due to the volume effects that I mentioned before. Then you can see sort of significant differences between these two analyses. I'm not expecting to see any huge differences in the extra radiation models, just because they're already pretty constrained, but it would be interesting to do this type of analysis as well, just to understand how much of the constraint is coming from the effects of priors in the Bayesian analysis. Okay, and then so I can just summarize. So it seems like extra radiation models are currently disfavored by ACT DR6, and so we wanted to understand if this is a feature of sort of all radiation models, or if, as we saw when fitting to Planck, if adding extra dynamics seems to fit better and allow for larger abundances of radiation, and then so also larger H naughts in particular. But it seems so far, just from the two that we've looked at, that's not the case. And so we still want to understand exactly what is the physics that's preventing this, just to understand if it's going to be a pretty robust constraint on any models that predict extra and effective. And then for the dark matter, dark radiation interactions, so even if you have minimal energy density in your radiation, you can still have significant effects on the power spectrum, of course. So dark matter, dark radiation interactions will still have observable effects. And to summarize, if you have a small fraction of dark matter interacting strongly, that effect will look like dark acoustic oscillations. And if you just have a weakly interacting sector, then you'll get a power law suppression of the matter power spectrum. And that cutoff will be determined by the mediator in this case. Yeah, that was. I mean, so EDE doesn't affect the dark matter directly. So this would be for models in which you're actually, yeah, changing the dark matter like interaction. So that would be a direct effect at smaller scales with respect to CMB lensing. I mean, so I think the idea before was that if, you know, if your late time matter power spectrum, if you could just map that to some CDM type matter power spectrum, then you're fine. So that's the rough heuristic we've been doing. But obviously, if you have you know, stronger changes in the dark matter interactions at those scales, it's not clear that Yeah, yeah. So it would be at smaller scales is the idea, yeah. Yeah, so yeah. Yeah, yeah. So the yeah. Yeah, so yeah, yeah, the main addition of ACT is that it gives um additional, yeah, constraints at smaller scales and with smaller error bars. It's mostly going to give constraints on radiation models, uh, whereas any drop of power on the CMB, yeah. So yeah, for the matter power spectrum, if you just have dark matter interactions, it's not going to constrain those as much, just because uh, in the CMB there's going to be degeneracies, so you're not going to directly probe that. So the constraint mostly for that will come from power spectrum measurements or structure measurements. Um, yeah, yeah. So yeah, so that's what I was saying. It'll change the amount of extra radiation you can have. hmm Yeah, yeah. So I think the sorry, that the data is, well, I mean, so even when you fit with ACT, you're obviously fitting. So ACT only has the high L data, so you're still fitting with Planck at the low L. So this is a combination of Planck and ACT. I mean, people will also use WMAP instead of Planck to at the low L, and there they're still seeing relatively consistent things. So um, mhm. Yeah, so it has, yeah, so just ACT alone will have very large error bars. Um, yeah, I mean, a lot of this is also, as I mentioned, sort of hard to trust here, just because if you have extra parameters, they're basically all insignificant here, because N effective is so small. So then you have this enhancement at zero N effective. So yeah, the 1D profiles are probably better for looking at those data constraints. Um, yeah. Yeah. So, oh, for these two. Yeah, I mean, so that's what I was saying. It's really because there's this sort of this I don't know if I put it in. Oh yeah. I guess, oop. Okay, well, I don't know. I mean, I guess you could still see it, but this is just sort of showing the fits to act DR6, and there's this sort of enhanced um, preference, and so that'll just sort of shift things. Even yeah, even if you don't have strong constraining power, but yeah, I mean, Planck didn't have any data there at all, so I guess that's just going to push it that way. We just haven't fit to SPT yet. I mean, I expect it's going to be the same, just because, well, SPT has less coverage, so the error bars are larger, and I think that's when they do the combined one, or just on its own SPT. I think the combined one, I saw the results were, because I think when I just looked at the SPT paper, they combined, yeah, with ACT and Planck, but SPT on its own had pretty big error bars, so I expect just adding it will give. I mean, we're planning to add it, but yeah. No, you could, yeah, you could get negative delta at effective. That would just be a different class of models where you couple to the photons instead. Um, uh, I guess we haven't looked at those because in respect to H naught, it would just make the problem worse. Um, but in principle, they would, yeah, fit that data well. Yeah, not in the CMB, but in the power spectrum. If there was interactions with dark matter, yeah, then you would still see that. It might be degenerate with sort of primordial effects as well, but I mean, I mean, yeah, you'll see a suppression in the matter power spectrum, which many models predict as well. So the feature will look slightly different. So I mean, in theory, if you had precise enough data at those small scales, you could distinguish. But yeah. Yeah. So in particular, dark acoustic oscillations you would still see because you only need a small fraction of dark radiation in those models. So those are really not as sensitive to the ACT constraints. Even if you just had a small ineffective, you could still see those features. Oh, S4, yeah, yeah. If Simons, yeah. I mean, I think S4 has projected similar sensitivity if it happens, but yeah, it would be good to see from Simons what the results are. Um,